For me, the debate has gotten a little bit heated, and it mostly misses the point. And sharing the conclusion up front, it's kind of a false dichotomy, because we're both trying to solve the same structural equation. We're both using regularization. We just package it differently. We're both facing the same data constraints, and neither can reliably identify specific effects from observational data alone. So the real question is not what's the difference between Bayesian and frequencies. The real data is how much of this is data versus assumptions. In fact, it can be mathematically proven that a ridge regression is mathematically equivalent to a Bayesian regression when that lambda is equal to a specific prior, which is a Gaussian prior. And you can see some Python code where basically I'm going to simulate some of this, and you can clearly see that with very simulated example, 150 observations in 5 channels, if you set the ridge lambda or the prior equivalent, you get exactly the same estimates. So essentially, at a very core level, we're both doing the same thing. Essentially, you're trying to regularize your parameters. Most of the channel priors in most models use the half-normal prior. The half-normal prior is basically used to ensure that your coefficients are positive, essentially. Now, the half-normal prior has a little bit of a problem. And this is admitted even in Google Meridian's documentation, which is you can never really get an estimate of 0. So even if your channel has 0 effectiveness, your estimates that are going to come out of the model are not going to be actually 0. This basically means that you can push weak effects upward slightly and get a sense of channel effectiveness that's not really there. But they do have an effect. And there's a little bit of a simulation here about prior dominance in small data, because this is another problem with MMMs. MMMs are a small data problem and also a very highly correlated data problem. And we get, so if you have like 8 channels times 4 parameters to estimate per channel, so we're talking about add stock and saturation and d beta and the standard deviation. Then you have the intercept plus a trend, you have seasonality, you have controls, you have noise. Then we're now talking about, in this example, 150 observations divided by 46, we then have 3.3 observations per parameter. We need to be careful when we're doing circular reasoning. Using, for instance, last click attribution results, or using, for instance, platform ROAS or platform conversions as a tight prior for your Bayesian modeling. If you're using those results as priors, then your MMM is not going to give you true data. It's going to launder your attribution data. So you're justifying, you just created a very fancy model that justifies your pre-existing data on attribution. If you're doing last click attribution, it's even worse if you're using that to inform, especially if you do it with very tight prior. Now, there are 2 claims that don't hold up, and they're two very common arguments. One argument I saw is that there is no uncertainty in the MMM. And this was to be honest, this was the statement that really pissed me off and made me do this lecture and this video and this entire research. But that ignores a little bit of sampling variability. First, if you ran that same quarter multiple times, you might not get the same result. Second, you don't have all variables in your MMM, so you're going to always have some admitted variable bias. So things are going to happen in the world that you can't control for. And third, there is always uncertainty in your estimates. And there's even a very interesting paper by Dew et al., which is very aptly titled Your MMM's Wrong, where they posit that you can have multiple model specifications, for instance, one that has non-linear effects and another that doesn't, that will both fit your data, they will both get proper accuracy, they will have opposite budget recommendations, and you don't know which is which. And you need to do a specific set of tests. What actually breaks an MMM, and that's the binding constraint, is obviously data quality, not methodology. And it is multicollinearity. And that is the bane of our existence. And the problem is, it doesn't matter if you're in a Bayesian or in a frequentist world, multicollinearity is going to affect you. It's just that it affects you in different ways. The end result is you can't tell those channels apart. There's one diagnostic that matters above everything else, which is prior versus posterior. And you can get this via any Bayesian framework. And this is a question that if you're using vendors, you should ask your vendors. Which is, if your prior and your posterior are overlapping, between the prior and the posterior, and on out of home, for instance, the prior is dominating. But this is one of the things that you can clearly tell if a model is behaving well or not, or are you cheating, or don't you have enough data to pull the model apart. What actually matters at the end of the day is span variability. Because if all of your channels are if you're spending the exact same amount in the exact same direction in a highly correlated environment, i.e. all channels go up and down at the same time, then there's no statistical technique that can help you. There is no statistical technique that can actually separate the effects, be it ML, AI. You can't separate if you can't tell it apart. So sometimes you need to do strategic span variations, channel pauses. I know it's really hard to convince, but there are 3 questions for any MMM vendor or for your MMM team if you're doing it internally. Where did your priors or your regularization parameters came from? If it comes from in-platform data or attribution, that's a red flag. How tight are your priors? And how much did your posterior move? Because if they're really tight, you have a problem there. And what experiments either validated the channel estimates, or alternatively, what's your test plan? This is the most common annoyance I have with people running frequentist approaches. Their claim of no assumptions, that's wrong. They have assumptions. They just have different assumptions.